Yeah, Pranav, you can start.
Okay. Do we have the ask the scientist session first, or do I do the talk first?
I think they are still in a session. They haven't yet joined, I guess.
Oh, okay.
Yeah. Rajita, have the children joined?
So, are you talking to Rajita?
Rajita?
Yeah, Hari Om Satyavati ji.
Children have joined?
Yes, I have asked them to join. 3 members will join. Three kids.
No, Pranav is asking what should be the first session like. Children will be asking questions.
Yes, they'll ask. Hari Om Pranav ji. Children wanted to ask questions related to science. So they'll come. I've shared the link with them. They'll come.
Okay.
So we'll start with the children. Great. That's a question. After that, next session.
I think they have joined. Samanyu and one more Chandrambike has to join. Samanyu, you can ask in the meantime. Samanyu?
How is gravitational force created?
How is gravitational force created?
Hey, you can remove the screen, screen sharing, and we can see this child's face.
Yeah, can you switch on your video, Samanyu?
So can you remove the screen sharing, Pranav? Okay.
Yes, I did.
Samanvi, can you come on the screen? Can you put her on the side window? Are you able to do that? No.
Satyavati ji, make me host. I'll spotlight her. Please make me host.
Yeah. So Pranav, you may be asked PhD, but I don't know whether you'll answer the children's question. How did gravitational force was created? Tough questions, okay? All the best.
Yes. Hi, Samanyu. Hi. You are muted. Can you unmute? Yeah, good. Okay. Tell me why you asked this question first. What is gravitational force according to you? Then I'll tell you why it's there.
It's like when you jump, it makes us fall.
Yes. So everything is actually attracted to everything. So it's like, I have a piece of foam here. Do you think this one exerts gravitational force?
No.
No. When I drop it, will it fall?
Yes.
If I have a comb, does it get attracted to you?
No.
No? Okay. So it turns out gravitational force is there between any two objects all the time. Even between you and this comb also, there is gravitational force. It's just that Earth exerts gravitational force so much that you're not feeling this comb getting attracted to you. So gravitational force is there simply because an object has something called as mass.
Please
So
mute.
if an object has mass, then it has gravity. Do you have mass?
Yes.
So does this comb have mass?
Yes.
Does this piece of paper have mass?
Yes.
All of them have gravity. That's why when you drop this paper, it falls. Now, which one has more gravitational power? The one that has more mass. So why does everything fall to Earth?
Because of gravity.
Yes, but which one has, the gravitational power is stronger if something has more mass. Any object that has mass has gravity. So if I have a comb and if I have a piece of paper, they exert gravitational force. So anything that has mass can exert gravitational force. But there's also the question of how much force it exerts. So the stronger the force is stronger when the mass of the object is very large. So between you and this piece of paper, which one has stronger force? Which one can exert stronger force?
Me.
Why?
Because I have more mass.
Correct. Now between Earth and you, which one will exert more force?
Earth.
Why?
Because it has more mass than me.
Correct. So what is the weight of the Earth? The weight of the Earth is millions and millions times more heavier than you. That's why everything gets attracted to Earth. That's why everything falls down towards Earth. Because the Earth is so huge. Now compare Earth to Sun. Which one is much, much, much heavier?
Sun.
That's why the Earth goes around the Sun. The Sun doesn't move much. Earth goes around the Sun. Between the Sun and the center of the galaxy, which one is much, much, much heavier?
The sun.
No, the galaxy is much, much, much heavier. That's why if you see our solar system is a tiny, tiny part of our galaxy called Milky Way. So Earth and the entire solar system moves around in the galaxy because the center of the galaxy is so huge. Much, much heavier than the sun. So it's all in terms of this mass. So which one is more heavier? That one exerts more gravitational force. So gravitational force is there as soon as between any two objects that has mass. It doesn't matter how small it is or how big it is. Everything exerts gravity, but the force is much, much greater when the mass is much, much larger. So that's how it is. So if you have mass, there is gravity. Good. What's the next question? Did you understand? Someone new? So between
Yes.
so are you exerting gravitational force on other objects?
Yes.
Yes, good. But why does everything keep falling to the earth? Why does it look like nothing gets attracted to you?
Because Earth has a more gravitational force.
Yes, because it's much
more
bigger.
heavy than me.
Exactly. Very good.
Wonderful, Samanyu.
Very nice. Now Chandrambike has a question, I think.
Yes.
Chandrambike, you can ask.
Does the gravitational force pull the layers of the Earth?
Pull the what of the earth?
Layers.
Switch on the video and come online.
Will it keep
Sorry?
it normally?
Pull what of the earth? Can you repeat it for me?
Does the gravitational force
Huh.
keeps the layers of the earth normal?
What is the layer of the earth? Can you tell me what do you mean by layer of the earth?
Inside of the earth.
So what are the layers?
Inner core, outer core, mantle,
Okay.
crust.
Okay. 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 So do you think these guys are moving around, floating around in space?
No, I mean, how do they keep it like an round?
Okay. Why are you always stuck to the earth? Are you moving? Are you
Gravitational-
floating around?
No,
No. You're always stuck to the earth. Why?
because of the gravitational force.
Yes. So in the same way, the mantle is also stuck to the earth. The core is also there in the earth. Everything is being kept together like a hard wall by the gravity.
Okay.
Yes. But I'll ask you one more question.
Okay.
So the air, right? The air around you, does
Yes.
it look like it's stuck to the earth?
No,
But is it really not stuck to the earth?
it is an element.
Yes. So
It
So
does
if you
not
look at the
contain mass.
tiny atmosphere, if you look at our atmosphere, it's gaseous, right? It's
Yes.
gases, right? So
Yes.
are the gases still attracted to Earth?
No, because it does not has mass.
No, gas has mass. So gas is made up of materials. It is light because the materials are spread around. So it's like, so if I drop this piece of comb and if I drop this piece of paper, which one falls faster to the earth?
That comb.
Why?
Because it was dropped first.
Okay. If I drop both of them together, which one falls first?
The comb.
Why?
Because it contains more mass than the paper.
But it contains more mass, but let's say I drop, yeah, it contains more mass. That is correct. But there's something called as resistance as well, air resistance. So there is air resistance that is making it fall, right? So the ones that are lighter gets attracted more strongly towards the earth, right? But nonetheless, even lighter things are also getting attracted to earth, right?
Yes.
So air, it turns out, is very, very light, but it still has mass. So it will still get attracted to earth. That's why even though there is atmosphere and it seems to move around, this whole gas, you can think of it as earth and there's some gas layer around, but this gas layer is still attracted to earth. That's why the atmosphere doesn't just magically vanish away. It's still there. Like you see air and everything throughout. If you go up to like 20 kilometers up in the air, you will still have atmosphere. So you would have learned about atmosphere, different layers also, right? Atmosphere, ionosphere, metasphere, exosphere, and so on. Have you learned that?
Yes, but I forgot.
Oh, okay. So these are different layers of the atmosphere. So they are still attracted. It looks like they can float around, but they are also still attracted because Earth is a huge, massive thing. So it will attract even the tiniest of particles around. Yeah. Good.
Thank you.
Next question.
Can I ask?
Yes, go ahead.
Okay, my name is not Supraja. I cannot change the name for some reason. So my
Okay.
name is Anirudh, and I have a question about the Big
Supraja,
Bang Theory.
Supraja, can you switch on the video and come online?
That's not my. Okay, wait. That's not my name though.
Yeah, that's okay. What's your name?
Anirudh.
Anirudh, come on, come. Yeah. Can you?
Okay. So I have a question about the Big Bang Theory.
Okay.
Big Bang Theory. Okay.
Okay. So so they say the explosion is still going on and the universe is still expanding.
Yes.
So there's basically nothingness after the universe.
So it's not nothingness after the universe. So it's like a balloon trying to blow up a balloon. So what happens is space in between two objects gets expanded. It's like that. It's not like there's a room and then there is something called as the universe, and then the universe is expanding more and more outside into the room. It's not like there's nothingness outside. Everything is there in the universe, and space between two objects is expanding. So
Yeah,
the
but,
space itself is expanding.
Yeah, but the other space that it remains like that unless the universe spreads there, like.
Yeah, so it's not like that. So that's the idea I want to say. It's like, so let's say you have a scale, right?
Yeah.
So you see there are markings on the scale. You see like there is 0 centimeter, 1 centimeter, 2 centimeter, 3 centimeter, and so on, right?
Yeah.
So what happens is over a period of time, this 1 centimeter becomes larger. The definition of 1 centimeter itself becomes 1.5 centimeter. So 1 centimeter actually becomes 1.5. That's what I mean by the inherent space itself is expanding. So it's not, so think of it like this scale, which is 30 centimeters long, will expand, and the definition of what is 30 centimeters will in itself become equivalent to a 40 centimeter scale, and so on.
So even though
that is, yeah.
So even the unexpanded part counts as the universe.
So that's what I mean.
What it eventually will become.
So there is no unexpanded part. So you have to think of it like the scale. So everything, let's say the whole universe is this scale, and the definition of length just becomes 40 centimeters instead of 30, and 50 centimeters instead of 40, and so on. So that is what I mean by the space itself is expanding. It's not like it's expanding into something. So it's not like the scale. So it's not like the scale is expanding physically by becoming larger and larger. It's just that the definition of space, the definition of what space is increasing larger and larger. So that's what I mean by space between two things is becoming. It's like unwrapping something. So there is nothing like expanding into another region. The whole thing itself, you have to think of it as the whole thing itself is unwrapping.
Oh, and also,
it's a bit complicated, I guess, to understand, but that is the idea. It's not expanding into anything. The whole thing inside itself, it's like between any two things is expanding. That's the idea.
Also, can the universe also contract? Because my teacher told me before the universe was formed, everything was like one small particle until some kind of reaction happened, and then it expanded.
Okay, it's not one single particle. Nobody knows what happened at the Big Bang yet, not even scientists. We just know our theory is still a bit incomplete. But what happened is essentially matter and everything just started blowing up from a very tiny point in time. So it's like it just started exploding. So now your question is, will it again go back and contract?
Yeah, and then form another universe.
Yeah, this is theory. So we don't have any experimental evidence yet as to whether that could happen. So there are many theories for the universe. So one says it will just keep expanding until it dies off. So there's something called as the heat death. So it will just die off. then the other thing is at some stage, it will say enough of expansion. Now I start contracting and it will start collapsing immediately. So that's called as the big crunch.
So like the exact science behind it is like not yet known.
Yeah, we don't know. We can't predict yet. We don't know what will happen. If you ask right now to any scientist, what is the fate of this universe? They'll say, I don't know. Because there are multiple theories and we don't know which theory is correct. So Big Bang has been the most successful theory of the universe, but we still don't know if Big Bang is actually the right theory. So there have been many other theories, lesser known theories that have been put forth, but Big Bang is known to be the most successful theory, and we do have a little bit of experimental evidence that Big Bang did happen.
Yeah, I also have another little question.
Yes.
It's about like in the Big Bang theory, my teacher told me there was something called she said something that like I don't know, made it the most like successful theory.
Yeah.
She said something about the red shift and cosmic microwave background radiation. I didn't actually get that. Like,
okay.
What does it like?
Okay. So have you, okay, if you stand on the road and let's say there's an ambulance coming towards you.
Yeah.
So, okay. So the ambulance has a sound. It's making kio, kio, kio sound. Right? So when the ambulance comes towards you, do you feel that the sound of the ambulance is getting louder and louder?
Yeah.
Okay. And then when the ambulance goes away from you, do you feel that the sound of the ambulance gets smaller and smaller?
Yeah.
Okay. In reality, is the sound changing for the ambulance?
In reality, it's like no, not actually, and it's like the distance.
So it's if it's approaching you and if it's going away from you. So if something comes towards you, the sound gets larger and louder and louder.
Yeah.
And if the sound, and if you go away from it, and if the ambulance starts going away, so you can compare at the same distance. It's not a distance thing. If you look, let's say 10 meters away, 10 meters in front of you and 10 meters behind you. If you compare the sound of the ambulance, it feels that the sound is larger when it comes towards you, and when it goes away from you, the sound is smaller. So this is called as a Doppler effect. So what happens is if something is approaching towards you, the sound becomes apparently larger. And if something is going away from you, the sound becomes smaller.
I left it from my laptop. I joined on the phone.
Okay. So the same thing happens with light also. So if light is approaching towards you, then light will up. So there's something called as, so so whatever you have for sound, there is an equivalent for the light version as well. So
I'll just give a pause.
in terms of colors, so
joining back.
Sorry,
he got dropped and he's joining back.
Oh, okay. Has he joined back?
Have you joined iPhone?
Yeah, it's me.
Yeah. Switch on the video.
Okay. Okay, so what happens is, if let's say you have green light, so do you know the spectrum of colors? There's violet, indigo, blue, green, yellow, orange, red.
Yeah.
Yeah, so let's say you start with green light. Violet is before green. So if there is light approaching you, it will shift more towards the violet side. And if it's going away from you, it will shift more towards the red side. So now everywhere in this universe, people observed this light shifting more and more towards the red, which means every object is moving away from you. So that's how they conclude. So this is red shift. It's just like the ambulance is going away from you. Every object is going away. So just like the sound is becoming fainter and fainter for you, every object is like that ambulance. It's going away, more and more away. If the light that you saw shifted more towards blue, that means you can conclude something is coming towards you, towards Earth. But everything seems to shift into the red region. It's like the ambulance going away. So if everything is going away, that means everything is expanding, right? So
Yeah.
everything is moving away from you. So everything is expanding. So that is how you show that things are expanding. And then based on this rate of expansion and everything, you can conclude something about the temperature of the universe. So this temperature of the universe is constant, and you can estimate it from the age and everything based on this expansion and everything. And it turns out experimentally you can find out that temperature, and you can find out that is there. That's the cosmic wave background. I'm not going into the details of that, but these are a few things that experimentally you can see, which is why the Big Bang theory has been successful.
Oh, thank you.
Yeah, but regarding the fate of the universe, we don't know yet. It could all end up in a huge expanded version, or it could suddenly crunch down, or there's something called as bouncing universes. So it's like expansion, contraction, and so on. So it keeps expanding. At some point it will contract, then it will again expand, then it will again contract, and so on. So it's called as the bouncing universe theory. Yeah.
Thank you.
Wonderful.
Good.
Very nice.
Very nice.
Ah.
Next question.
Next, Tejasvi R. Gowda. You want to ask?
Yes, ma'am.
Yeah.
Sir, you yourself said whatever has mass attract the things towards it.
Yes.
Sir, now if I go to the space
Yes.
and I keep a ball,
Mm.
side there it has to come towards me. But
Mm.
how it can come towards me?
So right now, is any object coming towards you?
Sir, I'm in the space now.
Yes.
I took a ball. I just kept it aside.
Yes.
Now it has to attract towards me, and it should come towards me.
But what if but what else is attracting that ball?
Sir, nothing else, because nothing else is there outside there.
So there are many other objects in space as well, right? So you are a tiny mass trying to attract that object. But even though you are very close to the ball, there is a huge amount of mass outside, like for example the sun. So it might be very far away, but it will exert a lot of force. Why would the sun exert a lot of force?
Sir, because it is it has more weight or more
Yes.
mass.
Yeah. So now what happens to that tiny piece of ball eventually in space is subject to all the masses around you and all the so this force that is exerted is a function of the mass, and it also depends on the distance between the two objects. So if something is closer to the object, it will exert more force. If something is far away from that object, it will exert less force. So now you are there, you're close to the ball, which means you have the capacity to exert more force, but your mass is extremely, extremely tiny. On the other hand, there is the sun, which is extremely, extremely large. So the reason why the ball is not getting attracted to you is because that you're simply not heavy enough for the ball to get attracted to you. That's it.
So then, if I have a biggest spaceship in the world, and like small ball in just the side of it, then it should get attracted.
Yeah, so you can think of it this way, no? So take this comb. So you bring it extremely, extremely close to your body. Will it get will it get attracted?
Sir, no, because of the gravity.
Of what?
Sir, of Earth.
Everything exerts gravity, no?
Sir, everything exerts gravity, but
Correct.
I am near the Earth. So
Yes.
very near the Earth, so Earth will attract it down.
Correct. So now, if you have an extremely big spaceship also, it depends on the weight of that spaceship, right? It's the same example that I showed you with the comb. So if there is something extremely massive in space, then it can get attracted. But it turns out even if you make an extremely big spaceship, it's still extremely small weight when compared to the weight of the sun. So that's why whenever you build satellites and everything, right? So think of it this way: the sun is capable of exerting so much force on Jupiter, on on these huge asteroids, on these huge planets, and so on, which are like extremely massive. Can you make a space shuttle of the size of the weight of the Jupiter, let's say? That's much heavier than Earth itself, right?
Sir, okay
But
then.
if you were to make a space shuttle extremely massive, then yes, the laws will hold. Like you'll have like a tiny. If you had a tiny ball, the tiny ball will start moving around you like the moon goes around the Earth.
Sir, then here Earth is there. I keep
Correct.
one magnet in my one hand, and I keep another magnet in another side.
Magnet.
Sir, two magnets.
Okay.
I keep it just towards its side. Then Earth should pull both down. But why
Both
they
the
why
magnets
they
down.
attract?
Both magnets down. Yeah. Very good question. Why does the magnet attract? Let's say, yeah, it need not be even two magnets, right? You had magnetism class today. So it can be a magnet and it could be some iron piece also. It will get attracted. No. Why? You should tell me the answer now. Why does something get attracted? You
Sir,
had magnetism class today.
sir, no, sir. I didn't have any class.
You didn't? Oh, okay, fine. Okay, then it's okay. Tell me why.
Sir, because they're magnets.
Yeah, so the thing is, the reason is, so the force, it's essentially simple. It's all just which force is stronger, right? So it turns out the force of magnetism is much stronger than the force of gravity. So gravity is a very weak force. Earth is still massive, and that's why everything falls down to Earth. But you need extremely high masses to actually exert so much force. But between two magnets, let's say one magnet and another magnet, the magnetic force itself is so strong. So that's why they can attract or repel based on the direction. They can either attract or repel. And that force is much stronger than the force of gravity. That's why these two can attract so fast and these two can repel. But the gravitational force between those two objects is extremely weak.
Sir, I have another doubt now.
Yes.
Sir, now the gravity is down there, and if
Correct.
I take a magnet and keep it up toward the opposite pole, then the magnet should fly high. Why it don't flies? Why it falls down?
Magnet opposite pole? Can you ask the question again?
Sir, here is the Earth.
Uh-uh.
Now, here is the magnet. Now here is the North Pole of the Earth. I'm at the North Pole of the Earth.
Yes.
I keep a magnet towards the North Pole. Now it should repel and it should be flying high, and it should even if it even falls, then it should turn and falls towards South Pole. Why it even don't even now even it falls towards the same.
Wait. North pole of the Earth is are you taking Earth as a magnet now?
Yes, sir.
Why is the Earth a magnet?
Sir, because Earth attracts like a magnet. Because Earth also attracts things.
Yes, but the law of attraction of Earth, gravitational Earth, and the law of attraction for magnet is different. So magnet has something called as North and South Pole, because of which it can attract or repel. Gravitational force doesn't differentiate. It says just attract, come to me. That is what gravitational force does. Magnetic force, magnets have duality. So like sometimes they can attract, sometimes they can repel. If I am north and you are north, they'll repel. If I am north and you are south, it will attract. But gravitational force is different. It always says attract, attract, attract. It doesn't say repel, repel, repel. So Earth has gravitational force, which will exert on the magnet. So there are two forces, gravitational force and magnetic force. These two are different. So Earth always exerts gravitational force on the magnet. And that's why no matter where you are on Earth, North Pole, South Pole, equator, wherever you are, it will exert the same amount of gravitational force on that magnet and it will say, come to me. The magnet, on the other hand, has North Pole and South Pole. And if it is North and North, then it will say repel. If it is North and South, then it will say attract. That is a different force, different kind of force. It is not gravitational force. It is, you can call it magnetic force. Got it?
I got it, but I got another doubt.
Okay. Yes. What is it?
So if you are in the space now, you're not even there in the spaceship. You're outside the spaceship. If you
Yes.
throw a ball outside, it'll go on till the end.
No. Why?
Sir, then if I keep a ball outside, then it should go and
Think of Earth as a big ball. What is Earth doing?
rotating around the sun
Yes. Why?
due to the gravity.
Yes. Now Sun is a huge mass and Earth is another huge mass, and because Sun is a huge mass, Earth rotates around the Sun. Moon rotates around the Earth. Why?
Because Earth is a huge mass than the moon.
Yes. So if you throw away, so let's say we have satellites. What are the satellites doing?
Revolving around the Earth.
Yes. So if you throw a ball, it will get so if you throw a ball, what will happen is eventually it will find a center of gravity like this. It could be some other massive object. It need not be Earth or Sun itself. Any massive object. So if you throw, it will keep going around under the influence of all of these different gravitational forces of all of these different bodies, until it will go and find a heavy object, a suitably heavy object, and then it will start revolving around that heavy object. That is what will happen.
Sir, then if I keep a ball there outside itself, and if I
Yes.
close my shuttle, then it will go somewhere and fast. Why it stays still there? It should go and attract towards some planet or towards something.
Yes. So it doesn't look like that because these things also take time, right? The speed that they get and everything takes time. So eventually it will go and settle. So for example, if you are in space, what happens is, so all of these take time. So there is also the scale of time, how much time it will go and get settled around and things like that is also there. So that time, because it's a very small object, that time is also gets extremely large and it moves around very slowly around. That's why you feel like it's just floating in space because the object is so small. That's it. So it is, in fact, at that point, no matter at what point, it is always under the influence of all of these gravity of all of these different objects. So based on that, things can move around a little bit, or things can get influenced very much, and all of these things will continue. Yes, go ahead.
If I came there after 10 light years,
yes,
then
so eventually, so it depends on how much time on it. So now you are going into math, you are going to the specifics. So you need to give me precisely what are the objects around that is influencing that particle and so on. So typically, let's say you just went, so it depends on where you are as well. So let's say you just went out of space, like we have the space station right now, right? International Space Station. So if you go there, it is still under the influence of Earth's gravity. So that object will just revolve around the Earth, just like how the moon is going around the Earth. This object will also. So that's why if you look in the space, because we have sent so many satellites, all the useless satellites and all the parts that have been broken off of satellites and everything, it's just floating in space. And they're all just revolving around the Earth. Just like the moon, they are also revolving around the Earth because they are also attracted to gravity.
Sir, okay then, why are they not falling on the earth due to the earth's gravity?
Why is the moon not falling to Earth if the moon is held together to Earth by gravity? Why is the Earth not falling into the sun?
Sorry to disturb. I think we'll give chance to other students also. You can type your questions in the chat box. Okay.
Yeah. So I'll just quickly finish this question. So
Okay.
it turns out. So there is some specifics into this, but I won't get into the details. So if things are head on like this, then they'll fall directly. But if it has a bit of energy that can go sideways, what happens is these things will start rotating around. That's why the Earth rotates around the sun and the moon rotates around it. And that is because of gravity. Yeah.
Okay, wonderful, Tejas Gowda.
Thank you, sir.
Okay. The last question, I think we have to wind up.
Yes.
Oh, Rupa, yes, Prabhu, she has raised her hands.
It is Megha, ma'am.
Megha, yes. Please switch on your video, Megha. Yes. This will be the last question.
I had a question that in
Yes.
few mechanical appliances like a fan and tube lights, it will
Yes.
be like there'll be two switches in for one appliance. Like if
Okay.
there is a staircase, there'll be a switch for the same bulb up and the same bulb down. Then if we turn it on at the down bottom of the stairs,
Yes.
then again if we go up and turn it on, it turns off. But how is that possible? Because this side it is actually passing, right? That side if we turn it off, how does it turn off?
So I guess you mean to say, like, I think you're talking about the two-way switch, I guess. So it's like, so did you mean like you are going to start climbing a staircase, then you turn on the switch, light turns on, then you go all the way up to the staircase, then you turn on the switch and it goes off. That is
Yeah.
what you mean, right? Okay.
Yes.
So it's essentially, so you can make so the way all of this is happening is, so the way a light will the light bulb will light is essentially if there's a current passing through the bulb. And when the current is not passing through the bulb, the light will turn off. So these switches are designed in such a way that no matter what you click, if you click once, it will turn on. If you click twice, so you click and then you click again. So it doesn't matter how you click. Let's say you turn it on and turn it off, or you turn it off and turn it on. So if you click it twice, then current will remain the same. Like, let's say initially you had current going through, you click it, current will not go. You click it again, current will go. You click it, current will not go, and so on.
Yes, sir.
So it is just essentially like if current is going or current is not going. So it doesn't matter. So if you click this switch here, current will go. And then if you go up and then click that switch again, current will stop. So it's just a matter of how many times you do the switching thing. So you click, current will go. You click, current will go off.
Sir, I asked the same question with my ma'am. She said that there is two different circuits for each switch. So
Yes.
if for one circuit we turn it on and another circuit we turn it off, how does the other circuit bulb also turn off?
So both circuits control the same bulb.
Yeah.
Okay. So so depending on what state it is, so it's like both circuits control the same bulb. So you can you can control that bulb using any of these circuits. So in one case, if I turn it on, it's making the full connection. On the other side, if I turn it on again, it will break it. So it's essentially both circuits. I mean, if I want to show it, I'll have to draw you the circuit diagram, I guess. But essentially think of it as both circuits control the bulb, and it doesn't matter what action you do where. If you do it once, current will go. If you do it twice, current will go off. And it doesn't matter if you do it in the same place or if you do it in this place or that place. If you do it twice, one here and one here, it's equivalent to doing it 2 times here itself. So that is how it works. That's how it works.
Okay, sir. Thank you.
Thank you, Megha.
Okay.
Question.
Is that it?
No, sir.
Yes, I think
Okay, go ahead.
we have done with this.
Gravity pulls down the things which have mass. Then
Yes.
birds have mass. How do they fly?
Yes. Aeroplanes also have mass. How do they fly? You make a paper plane and you throw it.
Yes.
They also have mass.
But after some time, paper planes will fall down.
When will aeroplane fall down? So you can so the gravity exerts a force. But if you exert a force larger than that force, what will happen? Why can you jump? You are getting pulled to earth, right? But
Yes.
can you jump? Why can you jump?
Because
So you can jump
control our-
because you can you can give force that is greater than than the gravitational force. That's why you can go up. That's why you can jump. So in the same way, for birds, they can exert a greater than that gravitational force, and that's why they can fly. Same thing with aeroplanes also.
Okay.
But you can't exert. So if you start flapping your hand down, you can't exert so much force. Gravity is for much is still larger. That's why you can't fly. If you do this, you can't fly.
Because I have so much mass than the birds.
Yeah, I have so much mass, so you have more force to overcome that. You have to give more force to overcome that, right? If you have more mass, gravitational force is also strong, which means you have to give more force to overcome, right?
Yes.
You are not able to give that much force.
Or you can
But when you jump, you can give that much force for some time. That's why you can jump.
Okay.
Got it?
Yes.
Good.
Thank you.
Good, like Pranavji, Kanti has typed one question in the chat box. If she is here, she can ask.
Okay.
Kanti.
So, Kanti ji, are you there?
Actually, Gayatri ji is asking Guruji.
Yeah. Gayatri, can you repeat the question? Kanti or Gayatri, can you repeat the question?
So, Pranav ji, many people from Vedanta talk about this wave particle theory, which, when they are explaining Vedanta. So, how is this wave particle theory connected to duality or Advaita, Dvaita?
Okay. Okay. So there is one approach that I always take when trying to compare science and Vedanta this way. So I, for one, when it comes to these, so there is physics that I know. There is Vedanta that I know a little bit, I guess. But what I do is I don't. What I do is I look at examples from physics, and then uh, I I don't equate these two things because I still feel equating these two things still needs a little bit of work. But what I can do is I can certainly compare things and draw a comparison. So comparison is different from equating things. So for example, it is like saying it is like something. We have, in English, we use simile. We say the eyes are as beautiful as the moon and something, right? So we are comparing the eyes to moon. It doesn't mean the eyes are moon, right? So that's the same approach that I have here. So in science, wave particle duality is essentially what scientists have figured out is that if you take any particle, it no longer behaves just like a particle. So a particle is, so there's something called as a wave and there's something called as a particle. Now a particle is like, let's say you're shooting a bullet. So it has a certain way in which it moves and you can pinpoint where the bullet is at all times. But when it comes to a wave, you're standing in the beach and a wave is approaching you. If you tell me where the wave is, I'll say it's everywhere, right? Because the whole thing is coming and moving towards you. So the wave is everywhere. But if you tell me where the bullet is, that's a particle, I can tell you exactly where the particle is. So this, it turns out every object in the universe behaves sometimes like a wave and behaves sometimes like a particle. So a wave is essentially, you can't pinpoint where the wave is, but you can tell which direction the wave is moving. Like you can always tell if the wave is coming towards you or if the wave is going away from you, right? But if you tell me where the wave is, I can't tell. I can't pinpoint and tell this is the wave because the whole ocean is approaching towards you. So every particle in this universe has this wave aspect and has this particle aspect, which is the confusing part, because how can something behave like I can pinpoint it and tell where it is, but at the same time behave as though it's everywhere? So this is the wave particle duality. Every particle has this wave nature attributed to it, and that is the wave particle duality. So now coming towards how you can take this to Vedanta. So the way I think of it is, so essentially, like our understanding of particle is incomplete because it sometimes behaves like a particle. It sometimes behaves like it's there at some point, and at sometimes it feels like it's everywhere as well. So this idea is this concept that something seems to be concentrated at some point, but that something is there everywhere as well is so this idea can be borrowed and can be understood in a deep way in Vedanta. So it's like it's essential for me, at least. It's like saying that aspect of that particle is present everywhere. It's not confined to a in space. So if you really think about things, it's not that things are actually confined. Things can be present everywhere. So this is the idea that I can borrow from this wave particle duality and bring it into the regime of Vedanta and try to understand it from there. Yes, I hope I've answered this question.
Wave behaves like a particle when observed.
Sorry?
Wave behaves like a particle when observed. The observer effect. No? We bring the
It's
Vedanta.
not just that. Yeah. Did I clear this doubt?
So yeah, Pranav, that brings me to this question where they say this observer effect and consciousness. where they say that the observer influences the behavior of the particle. So is the case with consciousness. Is this also related to the wave particle theory?
Yeah. Okay. Again, so when it comes to the wave there, so we need to actually try to understand what exactly is a wave and so is it like an wave, or is when I talk about a wave, is it something else? So, so the thing is, in so this wave nature of things and all of it came up because of quantum mechanics. So it turns out this wave nature actually is actually corresponds to it's not a simple wave, as in it's not like a simple wave that you see in the ocean. Instead, it is a what we is it's a the term that we use is called as a superposition. It's actually saying two things. So the way of saying two things are there at the same time, because you can't differentiate what. So just like in a wave, you can't differentiate where exactly the wave is. An alternative way of approach that is time. And
Your voice is
again,
breaking.
wave particle. Oh, can you hear me now?
Yeah, your internet seems to be weak. Voice is breaking. It's okay now.
Oh, okay. Again, wave particle duality, this observer effects are different things. I get into the details right now. Uh, Essential idea of observer effect. What you have is
Your internet speed is problem, Pranav. It's very weak, breaking.
okay. I have no idea. Let me just connect and disconnect, I guess.
Yeah.
Your voice is breaking.
Unless you are transmitting from Mars.
Okay, I just disconnected and connected.
Okay.
Let's see. Yeah. So I went to so many. I've talked about this. Can you say?
Pranav, it's breaking, Pranav.
No idea. Fine.
Can you switch off video and just talk?
Can you hear me now?
Yeah, we can.
Yes, I can. Can you hear me?
Yes, yes.
Oh, so about this observer, right?
No.
So just like I said.
Okay. Yeah, go ahead.
So like I said, it is two object. So thinking of two things, and it turns out when you observe, it just tells you which reality it has chosen. So essentially, as soon as an observer makes a measurement or makes a measurement,
So Pranav, your voice is not audible.
okay. Let me try to join my phone, I guess.
I think you can try from phone. This connection is breaking.
Okay, I'm trying to join from Okay, can you hear me? Okay.
Yes.
Okay.
Pranav, you can, is echoing. Are you on two systems? Just join on one system.
Yeah, I joined just my phone right now.
Yeah. Now you can.
Yeah. So
Can you come spotlight? Yeah. Good. So now you can speak.
yes, can you hear me now?
Yeah. You actually right now showed wave particle duality. Good.
So like I was saying, in the observer case, well, I think I was talking about the observer. Yes. So for the observer case, so again, like I said, it's not supposed to be taken one-to-one because again, the observer case scenario, we don't know if that is the right thing to talk about. But essentially, what it says is if you observe something, this wave nature breaks down and you see the particle effects. But it's not to be taken in a very literal sense as well. That's what I want to say. Like, please take it with a caution. It's not as it seems. It's but if you want to know more about these things, I don't want to delve too much into detail, but if you want to know more about these things, I've talked about in the previous talks, where I have gone into detail of what exactly is the connection that you can draw between a physics wave particle duality and the Vedantist way of thinking. But it's not a one-to-one equivalence. That's what I want to caution. Yeah.
So when you observe in the domain of physics, the behavior of the particle is changing. That is what the physics guys say, right?
No, it's not the behavior of the particle is changing. So it's always there. Wave nature is there. Particle nature is also there all the time for the particle. It's there. So what is a particle? It's not to be thought of as a bullet, or it's not supposed to be thought of as a wave. Both are there. So for example, if you take an electron, right? An electron sometimes behaves like a particle and it sometimes behaves like a wave. If you take light, sometimes it behaves like a particle and sometimes it behaves like a wave. You don't like, for example,
Okay, so when you're observing it, are you influencing the?
Yes.
Oh, okay.
So that's what I want to say. So what do you mean by observation? It's not like when you just see, because if you are seeing it, everything, like, there's no quantum mechanics about it. You are seeing the moon. It's all classical. There's no quantum mechanics there. What actually happens so this so this wave nature and this particle nature, right? It's exactly like the gravity thing. So the wave nature and the particle nature manifests when the quantum nature of that particle is strong. So like I said, this comb is attracted, or the scale is also attracted to you by gravity. But if you say the scale is going to come and fall towards me, that is absurd, right? It doesn't come and fall towards me, it falls towards the earth, right? So in a similar way, the quantum nature also manifests in particle. So every particle has an associated quantum nature with it. Just like how I can exert gravitational force on this scale, I also have a quantum nature as quantum aspect to it. But if I say I'm a quantum particle, that would be comparing to this phenomena of this scale being attracted to me. It doesn't get attracted to me. It falls to the earth. In a similar way, quantum nature gets manifested in in different quantum nature gets manifested in different things in different amounts in different ways. An electron is a proper quantum particle, a human being is not. So an electron will show all of these quantum nature, a human being will not. So that's why I want to caution you and say, don't take this as a one-to-one comparison. It's just like saying the scale, get this. So at the basis, the physics is the same. The scale is going to exert gravitational. I am going to exert gravitational force towards the scale because that force is always there. But will it get attracted to me? No. In the same way, every object has quantum nature. On what level, on what scale does this manifest? I don't know. Right now, uh, the quantum nature of a human being is extremely small. We are not like we definitely don't exert the quantum nature of what an electron exerts. Think of it that way. So an electron is a quantum particle and a human being is not. So when you say I observe something and that system collapses, uh, it's not because of it's not because of these quantum mechanics principles, at least. Yeah.
Yeah. Got it. A little bit, I got it.
My phone is also dying. Yeah.
Yeah, I think somebody else has a question, so I'll.
Yes.
It's there on the chat box.
Okay.
Sir, I have a doubt.
Yes.
I think Sannidhi asked first.
Ma'am,
Yes.
sir, sir, I have a doubt that
Your
when
voice is
we
breaking.
fire a bullet in the sky, upwards, for example, when honoring someone, we fire bullets in the sky. Why don't it land on the why
I'm
don't
sorry.
it land on the
Can you
same
repeat the
position,
question again?
which could also harm people?
Sannidhi, your voice is breaking.
Yes, sir.
Pranav, she has typed in the chat box.
Yes, typed in chat box.
We can refer that.
Oh,
I'll repeat the question again, chat box.
yes.
I'll type it again.
Yes.
Yeah, that's the question. About a bullet. Are you able to see the question?
Yes, I have a doubt that when we fire a bullet in the sky upwards, for example, while on someone, we fire bullets in. Who said it doesn't land? It does land. There have been cases where a bullet has come down, killed a person after going up. So the thing is, the bullet does land. It falls somewhere most of the time. So a bullet is a tiny particle. So most of the time it will avoid a human being, I guess. But yeah, it is not extremely safe to fire bullets to the sky like that. Because they will land at some point. So many things can happen on what kind of a bullet it is as well. Sometimes sometimes the bullets are very small, so because you give so much firepower to it, they can disintegrate and things. But yeah, bullets in general do fall on the land if you fire to the sky.
Wind speed makes a difference. A little bit of wind is there, it will fall somewhere else.
Yeah, all of that is affected, yes. But yeah, I mean, it will fall back to the land.
Sir.
Yeah, thank you, Sannidhi.
Sir, now, sir, is there any thing which repels the Earth's gravity?
Which repels the Earth's gravity. No, so that's what I'm saying. No, so gravitational force is always like, come to me, come to me, come to me. It never says go away. So gravitational force always says is always attractive. So gravitational force always attracts things.
So is there any other force which repels gravitational force?
No, so gravitational force is a fundamental force. So there are only 4 different kinds of forces in this universe. Every other force is a manifestation of this force. So the nature of gravitational force is attract. You can have other force, like for example, another kid talked to me about magnetic force, right? So that's a different kind of a force. So there is gravitational force that only attracts. Now this magnetic force comes under the domain of what is called as electromagnetic force. These things can attract and repel. So attraction and repulsion is coming essentially because of the nature of that electromagnetic force. But gravitational force in general can only do one thing, which is attract.
Sir,
Got it?
sir, is there any force which is called as repulsive force?
Yeah, so if something goes away, it's a repulsive force. So electromagnetic force is both an attractive force and a repulsive force. So it depends on what you are trying to do with it. You can make the force repulsive by like let's say you take a magnet. If you bring the north pole of the magnet to the north pole of another magnet, it will repel. So that is repulsive force. If you bring a north pole of a magnet to the south pole of another magnet, it will attract. So that's the attractive force. So it's the nature of the force. Is it repulsive or attractive? So any force in general is either attractive or repulsive. It can only do 2 things. It can either attract the 2 things or it can repel the 2 things. So it's another way of thinking about things. But yeah.
Sir, is there, like this itself, is there anything which opposes Earth's gravity?
Okay. So I said no, gravitational force is always attractive. So do you think there is a repulsive version of it?
So that's what I'm asking.
Yeah, so there is no repulsive version of gravity. Gravity can't repel. So gravity can only attract.
Okay, last question from
Did
Sunny.
did you hear about, because do you know, okay, I just want to ask you one thing. Do you know about dark energy?
Sir, no.
Okay, then good, Yeah, okay,
Sir,
good.
please
So
can you tell? Sir, please can you tell?
gravitational force only attracts.
Sir, please can you tell?
What?
Sir, please can you tell about black?
It's not black, it's dark energy. So there's something called as dark energy, which is a high level concept. You don't have to understand, but there are some cases where you can make the gravitational force repulsive.
Sir, how? Sir, how?
So if the mass of the object becomes negative,
So then how will we make it negative?
yes, you can't, right? So don't forget about it.
Sir, please, sir.
No, that's what. So if you can make the mass of an object negative, then you can repel.
Sir, that itself.
How do you make it? How do you make it? How do you make it? There are some regions of the, so mass, it turns out, is a higher level concept coming from something called as the space-time curvature. So now you can make some things to that space-time curvature to make it look like the mass is negative. And when that is the case, gravitational force can seem like it's repelling. That's the only scenario.
Sir, so that's a very high level concept.
Yes.
Sir, can you please explain it again? Means explain it more in simple words.
Okay, so this is why I didn't want to bring this up. So it turns out everything in this universe is kind of like a cloth. So the space and time is like a cloth. Okay. So let's say you have a bed sheet.
Yes,
So
sir.
it's a cloth. It's a cloth piece, right? So any object that has mass, think of it like you're sitting, you have put something heavy on that cloth piece. So the cloth piece was initially flat. Now the cloth piece became bent like this, right? When you put something heavy. So now if you put something on the side of it, what will happen to that object? Let's say you put a tiny ball on the side of that object. What will happen?
It'll of course slide down towards the
It will
large
slide
ball.
down and fall towards the ball, right?
Yes, sir.
Yeah. So what if instead of something like this, what if you had the cloth like this?
Sir, it would fall down. The ball will itself fall down.
The ball will go away, right? The ball will go away.
And the cloth will be
Right.
flat.
So if you have something like this, when you have a mass and the cloth is something like this, things will get attracted to that object, right?
Yes,
So
sir.
you have a cloth piece. You have a cloth piece like this.
Yes,
You
sir.
put something heavy on top, like you put something like this, it'll get folded like this, right? And if you put something over here, it will go and fall into it, right? But if it is like this, if you put something over here, it will go away, right?
Yes, sir.
Yeah. So any object that has positive mass will always make the cloth piece bend like this, and things will always get attracted to it. But if the cloth is like this, then things can go away, right?
Yes,
It
sir.
turns out gravity is like this piece of cloth. And any object that has positive mass, any object that has mass will always make it curl around like this. And that's why everything we wants to get attracted to it. But there are situations where you can make the piece of cloth curve upwards like this.
So how?
So then it will repel.
So then how? How to make it repel?
You can't make it. Only big objects can make it that way.
So can you give an example?
So the example is dark energy. It's called dark energy.
Sir, can you explain dark energy?
So this is what dark energy is. It makes things go upwards like this.
So then how to form a dark energy?
Okay. So how do you form an electron? How do you form? What is your name?
Sir, my name is Tejeshwar.
Sorry?
Tejeshwar.
How do you form a Tejeshwar?
Sir, by molecules, neutrons.
Yeah.
Photons.
So the thing is also made of things like that only.
So then how we will make it repulsive by dark energy? How to form the dark energy?
So it's made up of it's so you tell me how to form so you said you're made of electrons, right? How do you form electrons then?
Sir, I don't know, sir.
So it's essentially made of something like this. But yes, this is what dark energy is essentially. If I want to explain more, it would be more. I'll have to get more mathematical, and you won't be able to understand. But I guess this is the maximum I can do. Saying this is what this is what gravitational force does. It's essentially this cloth, and you put anything into the cloth, things can get attracted to it. So anything that has mass will get attracted. This is the nature of gravity. So it's like this cloth. Gravity is like this cloth.
Sir, okay then.
If you flip, sorry?
Sir, okay then how we can make the earth make like that?
Can Earth be made like that? Earth always has positive mass, right? So that's why it will always get attracted. Earth is not like that.
Okay,
So it's
sir.
like asking, can I make you fly? Can
Sir,
you fly?
sir, no.
Why?
Sir, due to the gravity.
No, but let's say you went to the moon or someplace and you started flapping your hands.
Sir, then I can mostly fly.
Yeah, so that means there's some reason why gravity acts stronger in some places, why gravity acts weaker in some other places, and so on, right?
Yes,
So
sir.
now you can't change. You can't, like, because Earth has mass, it does that. It's the nature of the thing. It's the nature of the force, right?
Yes, sir.
So similarly, this one's nature is this way. So any object, so the nature of gravitational force is this way. So if you make if you make the Earth, if you have mass for Earth, then it will like it will become it will become like this, and things get attracted. If you can make something which has negative mass, it will become this way. If you have something that is negative mass.
Excuse me, sir.
Now, how will you make Earth's mass negative? I don't know. You right now we scientists don't have an idea, but if you can think of something, great.
Excuse me, sir.
Yes.
Sir, I'm Tejeshwar's sister. I heard out the concept wherein you started with the dark energy part.
Yes.
Sir, and you told that mass, we have to make mass negative. But
Yes.
mass is a scalar quantity, right, sir? How, like mass can we take it as negative, sir? It's not possible, sir.
Scalar quantities can be negative.
Okay, so fine,
Why?
sir. Leaving the scalar quantities aside, mass, how can we take it as negative?
I'm saying you can make mass negative. So the underlying concept of a mass. So like I said, everything is this sheet of fabric, right?
Yes, sir.
So the way to interpret mass is through this sheet of fabric. So if this sheet of fabric curves like this, that means there is an object of positive mass, and it's curving like this. So mass is not. So this curvature is the fundamental quantity than the mass over there. So because it curves like this, there is mass.
Due to
Now if it
inwards, due to the curvature, which is inwards,
Yes.
mass exists at the center.
Yes.
So in the same way, you're telling that if the curvature is upside down, the
Yes.
mass outside on the curvature will have negative mass.
Yes, that's right.
So in the same way where you're holding now, no sir, in that if you take from the bottom inside, that will have
Yes.
positive mass.
Bottom inside over here.
Yeah, yes sir. There it will be attractive only.
No. So this is the curvature. And if you look at the curvature, it's always going to be negative on this one. That's how it's going to be. The curvature is always negative at this point. You can only define, there's only one curvature defined at every point. There are no two curvatures. So for this one, the curvature over here is going to be negative all the time. That's what the curvature is.
Sir, so from inside, we're not going to find out the curvature. Like, is it not considered?
No, so that's what I'm saying. So curvature is a quantity. There is no inside and outside. There's only one number curvature, which can be defined at every point. So the curvature for this one is going to be negative. This curvature is always going to be positive. That's how you define curvature. That's how curvature is.
Okay, sir. Sir, so since you explained all the curvatures part and told how the mass can be taken as negative, practically, did they find out anything regarding this, sir?
Yes, we do have experimental signatures of dark energy. We know what dark energy is, and it turns out the universe is in fact made up of, I think about 20% of the universe is made up of dark energy. Okay. This negative curvature.
Sir, which part are you specifying, sir, in the universe? Like, which part of it is considered to be dark energy?
I mean, it's everywhere in the universe. So you find regions of space where things seem to be negative mass. Things seem to be repulsive than attractive.
Okay, sir. So
it turned out at the early age of universe, there was a lot of it turns out this is just one theory. It turned out when the when initially during the initial stages of Big Bang, there was a lot of dark energy, which is why, and dark energy is repulsive, right? So it sends things out. So which was why the universe had a very early, there's an increased period of expansion of space early in the early universe. And people say it's the main cause of it is because of this dark energy.
Sir, I have another doubt.
Yes.
Sir, now there is a black hole in the space.
Yes.
It took off one whole galaxy.
It took off one whole galaxy. What do you mean by that?
Sir, means it took in whatever comes there. Then where will it go after it goes inside the black hole? Leave the black hole aside. I'm asking something else. Sorry, sir. Sir, he just meant to ask about the black hole. Like inside the black hole, where does it go after getting inside the black hole? Any celestial bodies?
Nobody knows.
That he should only know. So he's asking such a doubt, and I'm asking here something related to black energy. He brings up that.
Yeah, black hole people still don't understand black holes properly yet.
Yes, sir. Even they tell that there's gravity in black hole also. From where did the gravity originate? We don't know.
Oh yeah, gravity is always there. No, gravity is always there. The thing that we don't understand is, so this curvature I told you, right?
Yes, sir.
So the thing is, black hole is a very unique thing. So in a black hole, what happens is there is positive mass. There is always some mass and it's a finite number. But this curvature becomes infinity.
Okay.
That's the problem with the black hole. We don't understand it so well because it's the space-time curvature is infinite, and physicists don't like to deal with infinities in life. What it means generally is that the theory is incomplete. So that's why we don't know what happens there at the center. But it's positive mass. The mass is finite, but the density is infinite. So the curvature is infinite, but yeah.
So you're stating that mass, we know that is finite, but volume is infinite. We don't know that.
So it's not about volume also, but yeah, you can think of it in terms of
like
volume.
the space occupying whatever you're telling, sir. That part I just
that's what. It's not a space occupying anymore. It's an but you get the point. Yeah. Yes.
The infinity volume I was just speaking about. That's it, sir. The curvature part wherein you told that.
Yeah, the curvature becomes infinity. Yeah, the curvature becomes infinite. That's the correct thing.
Yeah, sir. The same thing, sir. You just wanted to tell something related to mathematics using for the dark energy, sir. What was that, sir? You didn't tell it to him. I wanted to listen to that.
So do you know integration, differentiation, how to solve differential equations and stuff?
Yeah.
Do you know how to solve second order partial differential equations and stuff?
Second order partial differentiation is not yet up, sir.
So I mean, I don't think you would know if I try to explain, but I myself don't know the full math, by the way. I am not an expert in that field. So but it will take a lot. So do you know tensors and stuff? I don't think you know about that. It will take time. So all of this needs high math. Some of the math even I don't know because I'm not an expert in that field. So I can't help you out there. I don't know it myself. If you want to know more, you should talk to a PhD person who is doing more science in this field. Which is so my area of expertise is called condensed matter physics. If you have questions related to that, I can answer it more at a more deeper level, I guess. But these things, I am not an expert, so I can't explain. I can't help you there.
Sir, so you wanted to explain the same thing, no, sir? Like the mathematics whole, it concludes by stating that the dark energy, wherein the curvature is inwards, mass is positive. Wherein the curvature is outwards, mass is negative.
Yes.
That's it, no, sir. The whole conclusion of the mathematics also deals with the same.
Yes. So whatever I have said, it's essentially math that I've tried to explain it to you in a simple way. Yeah.
Okay, sir. So that's the whole lot. That's how physicists or the scientists found out in the universe how that dark energy and things are working out.
Yeah. So essentially what you can see is you can find out shifts. So like those red shifts that I was talking about, you can measure those things experimentally, and that's how you can come. So actually, if you look at the universe, there is only about 5 or 10%, I'm guessing, of observable universe like Earth, Sun, galaxies, solar systems, and yeah, all of these things. 70% is something that we don't know. It's called as dark matter, and 20% is this, I guess, this dark energy. I'm not exactly sure about these numbers, but these are the numbers. So there's something called as dark matter, dark energy, and the observable universe. So whatever we can see with telescope, like whatever we can observe, is makes up only like a very small amount of space actually.
Okay, sir. Thank you, sir. Sir, sir, even
Yes.
now I also got a doubt just now.
Yes.
Now, sir, when the sun becomes more older and older, it becomes
Yes.
red giant.
Yes.
And after red giant, the sun also blasts like other stars.
No, it depends on the mass of the sun. So I think for the sun, what happens is it becomes a red giant, and then I think it will go down. No, what is it? What happens to the sun? Yeah, you tell me.
Sir, not a sun, sir. I'm asking about other stars, which becomes white.
Okay.
White, and it sends out all the particles which it has throughout the universe. Then now, if a black hole is there, after
Yes.
it becomes very big,
Yes.
will it get more bigger, or will it blast like sun and throw out all the things which has it has taken in?
Yeah. So there are multiple things that can happen to a star depending on what its mass is. So if it is something like the sun, I think it will just become red giant and then throw away all the objects out. There's something called as a neutron star. So what happens is the star completely becomes filled.
So Pranav, your video is stopped. Audio and video both are stopped.
Sir, I guess he's having some network issues probably.
So Pranav, are you there? It's frozen. Again. So Pranav, are you there? It's frozen.
Hello, can you hear me?
Yeah. Now it's okay. Go ahead.
Yes.
Okay. One also died out.
Sorry, sir.
Yeah. So I think I was talking about stars, right?
Yes,
So
sir.
depending on the mass of the star, it can do it can become this white, it can become this neutron star, and if things are even bigger, it can become a black hole.
Yes, sir.
Can you hear me?
Yes, sir.
Oh, okay, great.
That's
Yeah, so it depends on the mass of the star. So you can read up more on this. I don't want to tell, like, I think I'm eating up too much time of other people as well, I guess. But depending on the mass of the star, it can end in different stages.
Sir, I asked about black hole. After black hole becomes very, 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 very big, and it cannot hold more than
No,
it.
black hole doesn't become very, very, very big. Black hole always has the same mass. The mass of the black hole will never change. So what usually happens for a black hole is, so if you look at it, so it's coming back to your same question. Why does the moon doesn't come to the earth and blast into the earth?
ಕ್ಲೀನ್ ಮಾಡ್ತೀನಿ ಅಂತಾಳೆ ಯಾವಾಗ್ಲೂನು.
Why doesn't the moon fall to the earth? Why doesn't the earth fall onto the sun? in the center of our galaxy, Milky Way, there's a huge black hole. Why doesn't anything fall into that? So everything, if it is head on, it will fall. But if it has some speed in the other direction, it will just start circling it. So everything is just circling around the black hole. Things don't fall into the black holes right now. Like everything is stable, and all these things are just moving around the black hole.
Sir, that doesn't mean that after time, like if the time goes on, it circles around the black hole. Like actually, when you spin a ball with tied with a rope around your hand, it eventually turns out onto your fist, onto your wherever you're holding the center right now, sir. So the Earth and all the planets which are revolving.
Wait. If you are turning around the ball, why would it fall to the center?
Like won't it here, sir? I'm just speaking in terms of black hole, wherein black hole is attractive in nature. Sir, it attracts the things which is circling around it as well. Sir, what you said, the space-time curvature, now the black hole is in the center of the Milky Way, so the Milky Way, whatever the planets is revolving around it, then whatever is revolving around it, it should fall after some time inside the black hole. Yeah. That's what my sister is asking to you. Yes.
Will the Earth fall into the sun?
No, sir, that's not the thing I'm asking, sir. The Earth and the sun are like completely different. Right?
No, it's not. It's the same. With the black hole also.
Then sir, you mean that black hole is also having the mass like the sun, and the gravity is also same with the black hole as well?
Yes.
And sun, all the planets are revolving around the sun because of the gravity, and the speed it's revoluting.
Yeah.
And in the same way with the black hole also it's occurring.
Yes.
Sir, the black hole. Sir, what you explained. Sir, then like what you explained, space-time curvature. Sir, means what you explained like space-time curvature. Now this is a sheet. Now this is a sheet here.
Yes.
Means now you put a cube. Means it's actually a black hole. Which is like this.
Yes.
Now, if I take this thing, a medicine, and if I make it to revolve around it, after some years, it should even fall down because of the space-time curvature.
No, why is it falling down actually?
Sir, you do the curvature, of course.
No, it's falling down because right now in your thing, the reason it falls down is because Earth's gravity is acting on that object.
A black hole's gravity is also acting on it.
No, I'm saying in your example right now, the reason why things will fall down into that is because Earth's gravity right now in the sheet of paper that you hold. Right now in the sheet of paper that you hold, Earth's gravity is attracting. No, that's why ball is going and falling in.
So then even its gravity is also having
No. I'm saying no. I'm saying it's a wrong comparison because right now in that example you have another force which is Earth's gravity. Right now there is Earth's gravity which is being so when you do this example right now, when you put an object here, things will fall down into that because there is Earth's gravity. I mean that's what I'm trying to say. Like right now there is Earth's gravity.
Sir, if that Earth's gravity also, even the black hole has some mass of gravity. Then
I am saying in your example. So do this in space. If you do it in space, where gravity doesn't act so much, then tell me what will happen and tell me.
Sir, so basically, you're just trying to explain that the black hole's gravity, whatever it is there, upon that, the speed of the revoluting objects will, of course, won't fall into that due to the speed.
No, what I'm saying is his experiment is being done in Earth's gravity.
Sir, I'm not speaking about his experiment. He's completely confused with the things what he's doing. Since you were explaining there with the sheet of paper, he just thought about that. I'm just asking that you meant that at the center, whatever black hole is there, the Milky
Yes.
Way galaxy is revoluting around it.
Yes.
It is having some speed.
Yes.
So due to that speed, like even though the speed is constant all throughout,
Mm.
and the center of I'm going to say the black hole. This one, sir. In a sense, the black hole, though it attracts it due to the speed, it won't. It keeps revoluting, but it won't fall into that.
Yes, it's a stable orbit. It's just like the Earth, Sun, and Moon. So Earth goes around the Sun. Why doesn't the Earth fall into the Sun? It's this. If you find out this explanation for this, it's the same explanation for the black hole also. So it forms stable orbits. Everything forms a stable orbit, and everything is essentially just moving around that object. And the stable orbit is formed because of the gravitational forces.
Sir,
Yes.
sir, now dark energy is also applied here also then.
Yes.
So then it is also repelling here.
Yes.
So this is a very easy example
What? For what?
for black energy, dark energy, dark energy.
Where is it repelling? It's attracting, no? It's because of attraction that things are moving around.
So because of attraction, the things are moving around. But after
Yes.
it goes inside, because of the
No, it doesn't go
dark
inside.
energy
That is
repulse.
what I'm saying. It doesn't go inside. It
Sir,
forms
that
stable.
is the dark
Think about the
energy
Earth.
repulse.
Think about the Earth. Will the Earth ever go and hit the Sun?
So that is the sun also have some dark energy inside it.
No. Sun only has, there is no dark energy in the Sun. Sun is a positive mass. It exerts positive, attractive gravitational energy. That's it. Sun, there is no dark energy in the Sun. Sun is, just think of it this way, Sun is always a positive mass. Earth is always a positive mass. Earth always goes around the Sun. Earth will never fall into the Sun. It's a stable orbit.
That's it. There's no other question mark there.
Yes.
Okay, sir. Thank you very much, sir.
Same way, same example for black hole also. No difference.
Yeah. So then the black hole, the curvature is infinite means
Yes. What does
if
it mean?
anything inside it means can it take whole space inside it?
No. So that's what I'm saying. So there's a difference. So I don't know how to explain this more. So curvature is not the same as space. Okay, curvature is not the same as space. Leave all of that. Black hole is just like the sun. Think of it just like the sun. It's a bigger version of the sun, and it can do some special powers. It has some special things, but it's not doing anything to that. It's not. So it's space time. It's not just space. It's positive mass. Yes.
So
That's it.
all throughout basically, black hole is like a sun, but black
Yes.
hole can intake all the things which comes near it, but sun cannot.
Yes, that's correct.
That's the difference between black hole and sun. Sir,
Yes.
now in sun itself becomes a black hole in the future, then will it take all the planets? Black hole. If it becomes.
Sun will not become a black hole.
Sir, if it becomes a black hole.
There is no if it becomes.
Sir, if it becomes.
Okay.
Whatever questions you have, you can type in the chat box. Okay. We'll. I think it's time up. So, Prabhuji.
First of all, let us give a big round of applause to all the children for wonderful questions. So you have eaten enough grains of Pranavji.
Yeah.
Okay.
Thank you very much,
Another occasion, Pranavji, I will request one more occasion from you.
Yes.
More to eat your brain.
Yes, sure.
And a very good Tejas also is asking very nice, interesting questions.
So Tejas, you asked very wonderful questions. Okay, we will find out black hole and dark matter in the next series of talks with the Pranavji. He'll be coming prepared with equations, big equations.
I'll scare all of you guys with big equations.
Okay, sir. Okay, sir. I'm ready. Sir, it will be intimated in the group, no, sir?
Yeah. We'll be putting in the group, and thank you very much. Wonderful. So we'll give some time, maybe a month or two, and again we'll have a session with the Pranavji. Okay.
Like, is this being shared in the iLead Young Scientist group? That one, sir.
Yes. Yes.
Thank you, sir.
So, thank you very much. Thanks, Pranav. Okay,
Yes.
we'll catch hold of the children will catch hold of you next time. They'll eat your brain fully.
Yes. Yes.
Sadly, sir.
So, Pranav, you could not take up the topic which you wanted yesterday, right? Today, right?
Yes. We can have it.
We can have another session for that.
Yes, we can have another session.
Okay. Thanks, everybody. Have a good night.
Thank you, everyone.
Thank you,
Thanks,
sir.
everyone.
Very helpful session, sir.
Have a nice day, sir.
Yes.
Right, sir. Thank you, sir.